we're going to take a look at binomials. So binomial, bi meaning two, basically we're talking about things that have two terms. Bi, of course, meaning two. We don't really think of this as a binomial, but technically it's the most simplest binomial expansion of them all. 1 plus x to the power of 0, which of course is 1 because anything to the power of 0 is 1. Next one to the power of 1, we just get 1 plus. Now I know I don't normally write 1 as a coefficient, but I'm going to in this one because we're going to create a pattern. So 1 plus 1x. 1 plus x squared we know is 1 plus 2x plus 1x squared. We've also seen the perfect cube, and if we forget how to do it, we could of course just expand our 1 plus x squared with 1 plus x, and we end up with 1 plus 3x squared plus x cubed. Well, if I kept going, 1 plus x to the power of 4, I'll multiply that one by 1 plus x, expand it out, tidy it up. 1 plus 4x plus 6x squared plus 4x cubed plus x to the power of 4, and so on and so on. Now, there was this French mathematician, I think it was in the 1600s, I think it was, Blaise Pascal. Now he noticed a pattern, and it's what we now call Pascal's triangle. Seems to get all the credit. The reality is Pascal was not the first person to come up with this. Lots of ancient civilizations had recognized this. The Aztecs in South America, the Chinese discovered it many, many years before Pascal. I think the reason Pascal gets the credit is because of the patterns he found within the triangle. So we tend to call it Pascal's triangle. Here's the pattern. So 1, and then we write it this way so it forms a triangle. 1, 1, then the next row is 1, 2, 1, then 1, 3, 3, 1, and this pattern starts emerging. 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, and we see that, hang on, in order to get a number, we just add the two numbers immediately above it. So 1, 6, 15, 20, 15, 6, 1, and then we have our row for 7, which is kind of nice, the one for 7 when you look at it, because you've got multiples of 7 within it. There's one for 8, 9, and my personal favourite, I mean you probably have your own favourite, I know, but my personal favourite is this one, row 10. It's wonderful. Isn't that great? I mean, look at it. Look, right in the middle, 2, 5, 2, which is palindromic in itself and symmetric because 2, 5, 2. But then you go other side, you got 2, 1, 0, and then 1, 2, 0, same digits. How good is that? Row 10, got to be the best row. Okay, then we could keep going, and we have 11, and what the heck? Here's 12, and I'm pretty sure that's where I stopped because I kind of run out of room with the width. But you could keep going and keep going and keep going. Okay, so when we now expand out something like this, I can write it out straight away. I don't have to expand it out by multiplying 1 plus 2x on 3 times 1 plus 2x on 3 to the 6 and so on, because I know the pattern. We start off with what we call the binomial coefficients, those numbers in Pascal's triangle. So that's the first thing we write down. Then we just grab the first number, and it starts to the power of 7. And then you'll notice in each one the power goes down by 1. So the next one's 1 to the 5, 1 to the 4, 1 to the 3, and so on. But then we go the opposite way with the other term. So I've got 2x plus 3 to the power of 1, and then to the power of 2, and so on. The two powers always add up to be whatever the expansion is, in this case 7. So 6 and 1 gives 7, 5 and 2 gives 7, and so on. So there's the pattern. Still got a little bit of tidying up to do, but there's the expansion. Heck of a lot quicker than physically expanding the whole thing out. Now where's it really useful? It's really useful for something like this, because just imagine for a second that you're out shopping, you're in the shopping centre, and someone comes up to you, as they do, and says, oh, excuse me, you wouldn't be happening to tell me what 0.998 to the power of 10 is, but I only need it to 8 decimal places. Now, you don't want to look stupid, and you haven't got a calculator on you. Oh, no. But then you remember, hang on a sec, I can write 1.998 as 1 minus 0.002, and then I just substitute into the expansion to the power of 10. But because they only want it to 8 decimal places, I'll stop at cubed, because when I do 0.002 to the power of 4, well, expand that out to 8 decimal places, that's 0. And so every term after that's going to be 0. So I really only need to work these ones out. And they're pretty easy to work out, because you got 0.002, 0.002 squared would be 0.000004, and so on. And so, oh, there's the answer, and you can tell the person, and they say, thank you very much, and off they go. See, saves you being embarrassed in a shopping centre. And other wonderful uses as well, I'm sure. If I had to find the coefficient of x squared in this particular expansion, again, I don't want to expand the whole thing out, but I'll expand out the power of 4 using the binomial coefficient idea. So there it is, 4 to the power of 4, then it becomes 4 times 4 cubed 5x, and 6 times 4 squared 5x squared, and so on. But I don't want to expand the whole thing out, because I'm only interested in the coefficient of x squared. So I'm only looking for things that will give me x squared. So the 2 would be times this term's here. 6 times 4 squared, 5x squared. And then the negative 3x would be times the one that has 5x in it. They're the only ones that will produce x squared. I don't need to expand the whole thing out. So when I work that out, make sure you read the question. In this case it said, what's the coefficient? So they're only interested in the number in front. They don't care about the x squared. So getting all those numbers, it'll be 2 times 6 times 4 squared times 5 squared minus 3 times 4 cubed times 5, which turns out to be 960. Again, saves us time. We don't have to expand the whole thing out. All right, so 15a, playing around with these binomial expansions, you'll notice I've asterisked number 1 because we've already done it. Question 1 was writing out Pascal's triangle, but of course we've now got it in our notes.